Yes. These are instruments which are called moving coil instruments, right? Moving coil instruments. Now, what is a moving coil instrument? How does it work? We will see it in the next chapter. So don't worry about it. Okay, so next chapter, magnetism, electromagnetism. That's where we will study the moving coil instrument. You should be able to even see the coil inside. But we will learn about them in the next chapter. But right now, it is a moving coil instrument, and this is a voltmeter. It says DC volts. It goes from 0 to 10. So this is capable of reading up to 10 volts. And this is an ammeter of various ranges. That's why you have these. So this ammeter is not calibrated right. So the voltmeter, the ammeter is starting from 0, supposed to start from 0, and then it goes up like that. That's an ammeter, also a moving coil meter. You can see the moving coil inside. And this is the so-called galvanometer, which is supposed to be right in the middle. It's supposed to be right in the middle. And if a current goes this way, then it'll deflect that way. And if the current is going this way, then it's going to deflect this way. So this is more of a detector. And normally the galvanometer will be pretty sensitive, and therefore the currents are normally going to be in microamperes and all that. Not even milliamperes, but microamperes. So how the basic construction is that it has a coil. So here is a milliammeter. So the zero is here, and the highest is there. And the main brain behind it is the coil. So let's say the coil has a resistance of, say, 20 ohms. Let's say the coil has a resistance of 20 ohms, and the pointer is right there. Okay? So when a current passes through the coil, the pointer, which is attached to the coil, will deflect. So again, the construction of it will be seen in the next chapter. Right now, just understand it's a coil that can move. That's why it's called moving coil meter. So when you pass a current through the coil deflects, coil moves, and the pointer is also carried by the coil, and so it goes. So let's say this is 100 milliamp. It's a milliammeter. What's the scale? What's the range? The range is 100 milliamps. That means what? That means if 100 milliamperes comes in here, it will deflect fully. If 100 milliamperes comes in here, it will deflect all the way here, right? Can you just close it? Just close it. If 100 milliamperes comes into the coil, it will deflect all the way here. And if only 50 milliamperes comes in, then it will deflect it here. So that will be 50 milliamperes. If nothing comes in here, then it will be at 0. So it's like calibrated. Those things are calibrated accordingly. So it is now this one is calibrated to read 50 milliamperes all the way. Also, it can read 5 amperes. Now this has got multiple selectors. You can select which one you want to use. So this is a basic meter where you have a coil of 20 ohms. I'm just giving an example. 100 milliamperes flowing through gives it a full-scale deflection. So this milliammeter is also a ready-made voltmeter right now. Why? When 100 milliamperes goes through 20 ohms, how many volts is across here? How many volts? 100 milliamperes going through 20 ohms. How many volts is the potential difference? 2 volts. Yeah. So across here is 2 volts. That means what? If I supply, instead of supplying 100 milliamperes, if I connect it to 2 volts, will it read full scale? Yes. When I put 2 volts instead of sending a current, then it will read full scale. That means this thing is also a ready-made voltmeter, and I can say the ready-made voltmeter is 2 volts max range. So this is also 2 volts. So the same instrument, the milliammeter, is now going to act as a voltmeter of what range? 2 volts. So if I send only 1 volt here, it will come in the middle, and so on. This is about clear? So any milliammeter is automatically a voltmeter. So this milliammeter, if you're looking at the bottom one, this milliammeter is a ready-made voltmeter already. And so I'm showing you this particular example. This was a milliammeter of 100 milliamperes, but you can also look at that and calibrate it newly. So it's 1 volt, and here I can say 50 milliamperes. So if I'm looking at this instrument as a voltmeter, then when it comes here it is 1 volt, and when it comes here it's 2 volts. If I'm looking at the same instrument as a milliammeter, when it comes here it is going to be 50 milliamperes, and here is 100 milliamperes. Make sense? Now what we are kind of focused on right now is how do you change this milliammeter into an ammeter? Let's look at that first. So to change a milliammeter into an ammeter. So what is coming here? Let's say I want to change this one to an ammeter, and what's the range of the ammeter I want? Let's say 1 ampere. I want this to read up to 1 ampere, not 100 milliamperes, but 1 ampere. So if I want to make this one read up to 1 ampere, I need full scale deflection when it is 1 ampere, and 0 amperes is right there. Got it? So if I'm having 1 ampere coming in here, this coil cannot take more than 100 milliamperes. There's a limit for the coil to take, because if the coil takes 100 milliamperes, already it gets 2 volts. So 100 milliamperes in this coil is what creates full scale deflection. What if you send 1000 milliamperes through it? It is definitely going to burn out. This coil will burn out. And so you cannot let the 1 ampere go all the way inside here. You can only let 100 milliamperes go here. And you need to bypass, like a bypass surgery. You need to bypass how many milliamperes? Or how many amperes? 0.9 amperes. So look at this as 0.9 amperes and 0.1 amperes, then it makes sense, right? So this can only take 0.1 amperes through itself. And that means you cannot let all the 1 ampere go through the coil. Instead, we have to shunt it out. This is the word shunt. A shunt is a word that is used for parallel resistor. So I'm going to use this shunt in order to let this bypassing take place. So we cannot let everything go through here. We need to bypass what's coming through. But finally, when it comes here, it should be 1 ampere. We're not disturbing the current. An ammeter is not supposed to disturb the current, right? So the current that's coming in and the current that's going out is the same. The only thing is we are not letting more than 0.1 ampere go here. So 0.9 ampere has to go here, such that the potential difference from here to here maximum should be what? 2. If the maximum potential difference is going to be 2 volts, how much should be this resistance? What resistance will I choose there? Because I have to choose a resistance such that 0.9 amperes will flow through itself. So what should be that resistance? So all you do is 2 divided by 0.9, that's the answer. So how many ohms should this be? How many ohms should this resistance have if I need 0.9 amperes to be passing through it? Yes.
2.2 repeating.
2.22. So 2.22 ohms, if I put here, automatically this milliammeter, which was having a range of 100 milliamperes, is converted to an ammeter of range 1 ampere. Now suppose I have 10 amperes coming in now. Let's see what changes have to be done. Suppose not 1 ampere is coming here, but 10 amperes. So now I'm going to calibrate it to 10 amperes. So if 10 amperes is running in here, how much is allowed through this section? 0.1. So the rest of the 10 must go this way, which is 9.9. So 9.9 amperes going through this resistance should drop the same 2 volts. This cannot take more than 2 volts, by all means. So 2 volts divided by 9.9 will be the new resistance. So this is the resistance for a range of 1 ampere. And if your range is going to be 10 amperes, what resistance will you choose? 0.20. Whatever. So if you choose this resistance to be this many ohms, which basically is a wire, you can just use just a wire for that action. You can see they have connected resistors inside. That is a shunt that you're seeing there. Resistors are inside, and they are shunts. So using resistors in parallel will convert a milliammeter into an ammeter of different ranges. Can I change this into a 100 ampere instrument? Nothing. It's easy. 100 ampere coming in here. 0.1 goes here, 99.9 goes down here. So 2 divided by 99.9 will give you the new resistance, which is just a thick wire. And that will make this same instrument with the same pointer and the same coil read up to 100 amperes. Make sense? So you can use this method. Now if you want to use it in multiple ways, all you need is a switch. So this is one resistance of 2.22, and then this is another resistance of 0.202, and you can have one more resistance for the 100 amperes. So you have all these contact points, and the incoming current is coming from here. This is permanently connected here. Now I need these connected to each one separately. So I have this. Alright, so if this pointer is here, it will read 100 milliamperes. If this pointer goes here, it's going to be 1 ampere range. So I'll put 100 milliamperes range, 1 ampere range, and if I flip it here, it's going to be 10 ampere range, and if I flip it there, it's going to be 100 ampere range, like that. Okay, so it's a rotary switch that you can use to change it to different ranges. The basic thing is 100 milliamperes, and then you change it to different ranges. So a simple milliammeter can be converted into an ammeter of any range by just using these additions. Get it? Now let's see how the same milliammeter, which was an automatic voltmeter. So this was a voltmeter, right? What is the range of the voltmeter? When I connect 2 volts here, what will it read? It will read 2 volts, full range. Correct? So if I connect 2 volts, it will read full scale. Now, if, for example, the voltage that I want to check is much more than 2 volts, let's say 20 volt range. So if I want to calibrate a 20 volt range, so which means basically I'm going to put 20 volt here. So if I want 20 volt connected and I want full scale deflection there, I can't connect 20 volt here because 20 divided by 20 is how many amperes? 1. This can only take 0.1 amperes. If anything goes more than that, it's going to burn this coil. So what can be done? This is 20 volts. I don't want more than 0.1 amperes going here. So in other words, I want to control the current to 0.1. Or in other words, this can only take 2 volts, but I have 20. What should I do? I have to drop off 18 volts elsewhere. For that, you have to use a series resistor. You have to use a series resistor. What resistance will you choose here so that 18 volts is dropped off at a current of 0.1 ampere? At a current of 0.1 ampere, you want 18 volts to be dropped off. How much resistance will you have? Huh?
180.
180. So the resistance you're going to choose is 180 ohms. Why? Because 18 volts at 0.1 amperes. So what's the resistance? So 18 divided by 0.1 is 180 ohms resistance. So if I put 180 ohms resistance here, it's going to work as a voltmeter of what range? 20. Now if I want to change this one to 200 volts range, that means imagine I'm going to put 200 volts here. How many volts should you drop off here?
1800.
No, 2 volts here. So out of 200, how many volts should we drop off and not let go here? 198. So that means you have to put a resistance such that 198 volts are dropped off. So what resistance will you choose? 198 divided by 0.1, which is 1980. You get it? So now when I put 1980 ohms resistance here, this same instrument is now capable of reading up to 200. So if I don't put 200 but 100, then you'll come halfway. So basically it's the same milliammeter that's working as a voltmeter of even different ranges, all by the use of these resistors. So you can decide what resistance you want to choose. Now suppose the voltage is 2000 volts.
19,980.
Yeah, 19,980. So the resistance you're going to choose is 19,980 ohms. So if I put 19,019.98 kilo ohms, basically, if I put that there, the same instrument is now capable of reading up to 2,000 volts. Full scale deflection is 2,000. Halfway, it's 1,500, like that. So the same instrument can be converted into an ammeter of different ranges, a voltmeter of different ranges. You get it? Even here, you can choose your ranges like this. This is 1980. Yeah. So if I have this kind of a resistance combination, what's this? Here's a selector. You don't have to worry about this now. Okay. So between, these are the terminals. These are the two terminals. Positive terminal, negative terminal. You have seen those terminals, right, in an instrument? Positive lead and negative lead. This is what it is. This is the red wire. This is the black wire. Okay? Now, if I connect this over here, what range of voltmeter are you using? If I connect this one here, what's the range of the voltmeter? 2 volts. If I connect it here, the current is going to go like this and go like that. Now it is 20 volt range. If I connect it here, the current is going through 1800 and then through 180, so total is 1980, correct? And now that is the 200 volt range. And if I connect it down here, it's going to go through all of this, which is 19,980. So that will be 2000 volt range. So all by just turning some of the knobs, you can change the same instrument to different voltages. Make sense, Raymond? Now, the same instrument now can also be used as an ohm meter. What's an ohm meter? Something that measures ohms, yeah. So the same instrument can be used as an ohm meter. This is how it goes. Now here are the terminals. The red terminal and the black terminal. And you have a battery inside. So this is a device that will need power. So without a power, it won't work. So you need a battery inside. So let's say I put 2 cells in it. So this is 3 volts. I put 2 cells in it, and that's 3 volts. But you know that this cannot take more than 2, and therefore I need to put a variable resistor here. I need to put some variable resistor here, and then it will be just right. So if I put a variable resistance here, it's possible that I drop 1 volt off here, and that means if I connect these 2 leads together, it will get 2 volts, and so this pointer will go all the way here. When the pointer goes all the way there, what resistance have I put across these terminals? If I just join the terminals like that, what's the resistance? If I take the 2 wires and just touch them together, what resistance is that? 0. So when this goes full scale, I'll mark this as 0 ohms. Make sense? When it goes all the way there, I'll mark that as 0 ohms. And when I don't connect it at all, what's the resistance when I don't connect at all? When the leads are open like this? Infinite. That means here, I will not put 0, but infinite. So now it's an ohm meter. If it's open, then the pointer will be here. Close it, and the pointer goes there. Do you understand how the ohm meter works? So when you connect the 2 terminals like that, you are pushing 0.1 amperes, and so it will read full scale, and that is what we're going to mark as 0, because when you connect the 2 terminals, you're not connecting anything there, 0. But when you open it up, it is supposed to be infinite. Okay? Now what if I connect 20 ohms here? Suppose I connect 20 ohms. What's going to be the current? Let me see if you can guess it right. When I connect 20 ohms here, these 2 together are supposed to get 2 volts. When I connect 20 ohms, the current is going to drop down. Okay, you're dropping off something already here of 1 volt. So already 2 volts are going to be across these 2, right? So when you join them together, it's going to get 2 volts. But if I put a 20 ohms resistance right there, and then what will happen is the total resistance is doubled now. So the current from 100 milliamperes is going to come down to 50 milliamperes. So I will put a mark over here and say 20 ohms. I'm calibrating it. I know this is 0, and that is 20. And obviously 10 must be somewhere there. So you can actually connect 10 ohms and calibrate it. So you can actually put the calibration. So that's 10, and that's 5. And it goes like that. It's not in proportion. It's not in proportion. We need to close that. It's not in proportion. So it'll be like 1. It is not in proportion. You can see 1 ampere goes all the way here. The rest of the 4 is only pushing it this much. The rest of the 5 is pushing it a little. And the rest of the 10 is pushing it just a little only. Now, if I put different resistances here, this is going to change. So probably from here to here, it may be 50, and then 100, and then 1,000. You know, it goes out of proportion altogether. So it goes like that, and finally when it comes here, it's maybe like 10 mega, and finally it's infinite. So if I put 10 mega ohm, it will possibly come here, a tiny current. If I put smaller resistances, the pointer is going to go there. If I put 0, it will get full scale reflection. So this scale is not a linear scale. I wish I had brought that one. You can see the scale is pretty not linear. So initially it will be like crowded lines, and then after that kind of opens up. So that is called an ohm meter. Now once this scale is calibrated, then all you need to bring in all you need to check the resistance of something is just put whatever you have right there and read what it is. But these days they don't use these instruments. This sort of analog devices are gone. Everything's digital now. So the brain behind it is still the same thing, but instead of moving coil meters, we are having a digital approach to the same thing. So moving coil meters are very rarely seen. It's not too much, but still they use it. Still some of the aircraft controls and the meters are all like still analog. So it's still there. It's not completely gone. The analog meters, the ohm meters need a potential difference to work, but the voltmeters, ammeters, they don't require a voltage to work. They work because they are that. Now the digital meters, they don't work by itself. You need a power supply, and depending on the power supply, then it'll work. Now if the power supply goes down, it becomes poor battery, weak battery, and then whatever current or voltage is going to read, they're all wrong. So the moment the battery sign indicates that it is weak, you need to change it, because with a weak battery, it's not going to read the right current, the right voltage, nothing. But in this case, it's not that, Yeah, right now it is not reading 0. And all you need to do is put a screwdriver here and then twist it and then change. See it's changing? Right? So we change the pointer and bring it back to 0. Oh, 0 is right there. I forgot. Yeah, 0 is there. So you need to take it there. There it is. Kind of close. 0 is here. So a galvanometer is something that is... Now if you put all these things together, the ammeter changed into different ammeters. The voltmeter selected to different volts. And the ohm meter, all this together is called a multimeter. So in a multimeter we have all these things. All you do is just turn the knob and select whatever. So the knobs that we actually kind of turn around is mainly turning it to select whether you want to read the current or voltage and what range of voltage and what range of current. That's basically it. Okay, let's work some problems on capacitors and Kirchhoff's laws combinations. I already told you what is Kirchhoff's laws, and so you should be able to work these things out. All right, let's do this. It may be a little hard, but it's okay. I'm working for you. Two resistors and two uncharged capacitors are arranged as shown in figure. So I'm going to draw that figure first, and then I'll read out the problem. Right, AB has switches as 8.8 ohms, 4.4 ohms, 0.48 microfarads, 0.24 microfarads. That is the circuit diagram. Let me read it. So two resistors and two uncharged capacitors connected as shown. Then a potential difference of 24 volts is applied across the combination as shown. Question A. What is the potential at point A with switch S open? What is the potential at point A with switch S open? Now, You've heard the word potential before. What's potential? With respect to? Potential is what? The word, yeah, it's true, but potential, like if I say, oh, this has got a potential right now of 50 volts, what does it mean? With reference to what? Okay, define potential. Define potential, electric potential. Yeah, we've written it already down. Just define electric potential. You should be able to see that. It's the amount of energy needed to move 1 coulomb from infinity to that point. So the total work done with respect to infinity is that. So when you say 50 volts is the potential right here, it is 50 volts with reference to a 0 volt. Correct? Now in this case, this is our negative terminal. This is going to be our ground terminal or reference terminal. So this is 0 volts, this is 24 volts. You get it? So this side is 24 volts positive with respect to this side, which is going to be our 0. So with reference to this line is what they're asking you. That's why they said, what's the potential at A? Which means basically they're asking what's the potential difference from here to here. Simple. Yeah.
Is that 4.4 ohms?
Yeah, this is 4.4 ohms, this is 8.8 ohms. So how many volts is the potential at A? You can actually look at it and go by proportions and answer the same question. Just go by proportion. You don't have to sit down and calculate. Use just common proportions I use. Now switch S is open, right? That means just ignore this line. Totally ignore that. And capacitors, ignore them for the time being. Because what are the capacitors going to do? Yeah, they will receive 24 volts. That's a totally different section, but this from here to here is together 24 volts, correct? So how many volts should be here?
24. Or no, 16.
16?
Is that good?
16? It'll be 8. The bigger resistor picks up more potential drop than the smaller resistor. So in other words, the 24 volt is going to be distributed in the ratio 2:1. Right? You understand that? So if you want to do it by actual calculations, yeah, go ahead. What is the total resistance of this section? 13.2. So 24 divided by 13.2 gets you the current through both of them. So 13.2 times 4.4 is the potential difference here, which is 8. From here to here is 8. From here to here is 16. But when you're asked what is the potential at A, you're referring not to this terminal, you're referring to this terminal. So this is 8 volts. And this is 0 volts. And that is 24 volts. So you can see clearly there's a drop from here to here of 16 volts and a drop from here to here of 8 volts. Make sense? Okay. That's the first part of the question. Then they're asking you, what is the potential at point B with switch open? Now they're asking for this potential with switch open again. So since the switch is open, ignore this section completely. Because this set of capacitors are going to get 24 volts from here to here. If this is 24, isn't this 24? If this is 0, isn't this 0? So both these capacitors are going to get a total share of 24 volts. But you have to find out how much is here. And that is going to be the potential at B. How much is here? How do you do that? What's the procedure of doing that? You need to find the equivalent capacitance of these two. What's the equivalent capacitance of these two in series? Product over sum. These are in series. So you do product over sum. What is 0.48 times 0.24 divided by 0.72? 0.16. So 0.16 is the equivalent capacitance, and how many volts supplied there? 24. So what's the charge on each plate? On each capacitor?
3.84
microcoulombs. Yeah. So the total equivalent capacitance is 0.16 microfarads, and the total voltage applied is 24. So times 24 will give you the Q in this entire section, and because they're both connected in series, they both receive the same Q. How much is that? 3 microcoulombs. This one is 3.84 microcoulombs. So if this is getting 3.84 microcoulombs and this is the capacitance, what's the potential difference? Q is equal to CV. So potential difference V is equal to Q over C. 3.84 microcoulombs divided by 0.24 microfarads. How much? Do that. 3.84 divided by 0.24. 16. Exactly. So the potential difference here is going to be 16. So definitely this must be at 16 volts. Make sense? This is 24 and this is 16 and that's 0. So basically this whole capacitor gets 16 volts. Whereas this capacitor is only getting 8 volts. From 24 to 16 is only 8 volt drop here. It's a bigger capacitor, but only 8 volt drop. It's a smaller capacitor, but it has got 16 volt drop. Okay? So how we did it. Next question. When the switch is closed, what is the final potential of point B? When the switch is closed. So all this is okay so far. We treated them independently. Now when the switch is closed, what's going to happen? You can look into this also. What is the potential here? And here? As soon as you close the switch, which way do you think a current is going to flow through the switch? This way or that way? Yeah, because it's a higher, this is a higher one. So the current is definitely going to shoot off this way. So let's say now the switch is closed. When the switch is closed, now you're going to find out how many volts is across B. Across B, on B. How do you do? The switch B is closed. So what is the potential at B? You must be able to answer this straight away, actually. How much? To better understand this problem, look at this. I'm just changing the circuit a little bit. Is that the same thing?
Yeah.
It's the same thing. So basically what's happening here, there is a capacitor connected across each one independently. That's what's happening. When the switch is closed, this is basically the story. And point A and point B are the same. Because you're closing the switch means that whole section is going to be the same. So point A and point B are exactly the same. So if you want to find the potential at A, B, find the potential at A, it should be the same. Alright, now how do you tackle this problem? How many volts are supposed to be here? 8. Because the current that's going to flow here is non-stop, it's continuous. Non-stop current is going through this. But these capacitors will pick up charges depending on the potential difference permitted for them. So how many volts is this going to get? 16. This will get 16 volts, unlike before. What was the voltage before? 8. Now it's going to get extra voltage. That means what's going to happen to this capacitor? Get more charge, right? Okay, so this will get 16 volts. And this will get the potential difference across here, which is 8. So this is going to be 8. What was the charge here before? What was the voltage here before? Now it's going to drop to 8. That means this is going to discharge. But that is going to charge up. Get it? But anyway, the answer to this question that I asked, what is the potential at B, is simple, 8 volts. That's 8 volts. The next thing says, how much charge flows through the switch after it is closed? After the switch is closed, there is a rush of charge. So let me push it back again to the other picture. When the switch is closed, the current is going to be moving this way. Charges are going to rush this way. And why charges are rushing this way? Because this is in a charging cycle. So basically this is what's going to happen. And this is going to be a discharging cycle. So this is going to be removing its charge and go that way. So because the potential difference across here was higher, 16, so it's going to push it that way. So this is going to drop, that's going to go up. Make sense? What's the new charge across here? You can do that because you know the capacitance and you know the voltage. What's the new charge?
7.68.
7.68 microcoulombs. So it has doubled the charge now. And what's the new charge across here? 1.92 microcoulombs. So the charge on this has gone down to 1.92 and the other one has gone to 7.68. And this was initially charged plus minus and plus minus. So this one has lost its charge. How much charge did it lose? How much charge did it lose that went off this way? Because that's the way it has to go. That's the only way it can discharge and go. Because this was carrying 3.84 microcoulombs. Now it has to drop off to 1.92. So the charge is going to this is going to discharge through this. This is going to charge that way. So what is going to be the total charge that's going to flow through the switch?
9.6.
How much?
9.6.
No. This was 3.84 and it has grown to 7.68. So how much charge went this way? 3.84. And this one is shedding off some charge. And so how much is going this way?
1.92.
So what is the total?
5.76.
That is the answer. So 5.76 microcoulomb is rushing through the switch so that it will get its new charges. Got it? Okay. So just to make it clear to you, various points, like what is potential, and how do you treat this section, and how do you treat that section. So a combination of resistances like that is called a potential divider. Now you see how it's dividing the potential? It's called a potential divider because you have 24 volts and I need only 8 volts. This is the way to divide it. You divide the potentials. Get it? A typical potential divider is this also. That's a long resistance. And you can tap out one section of it. You can slide this up and down. So this is a potential divider. So if I connect a voltmeter here, how much it's going to read depends on where you connect it, right? If I connect this terminal here, how much is that voltmeter going to read? Nothing. 0. Because there is a 24 volt potential drop from here to here, but this voltmeter is connected to nothing, and therefore the voltmeter will read 0. If I move this wire from here and put it here, how much will that voltmeter read? 24. So if I drag this terminal to exactly in the middle, how many volts you can get? 12. So that's how you divide the voltage. You can just change the voltage accordingly. And this is the kind of thing that's used in your volume control. What is this volume control thing? Volume control is you have a signal coming from here, which is pretty strong. A signal that's coming from here is kind of strong, but I cannot let all of it go into the amplifier and amplify it the same way, right? So what do I need is I need to tap this out, and this is what I will send it to the amplifier. This is the amplifier. And the output of the amplifier is your speaker. Okay? So if I don't want too much sound over there, drag this down. So you're controlling the volume. You drag it all the way up, you're blasting it there. Okay? So semiconductor types are different. Now this, you can see the coil here. A very fine coil. It's pretty shiny, it passes around. And you can see there are 1, 2 terminals. So this terminal and this terminal are these two. And the middle terminal is the one which is connected to this. So when I move it like that, I'm tapping different sections of the same coil. And this will make it better to understand. Here it is. Can you see this terminal is here? This one is here. And this is the one which taps. And where is this wire coming from? This one. So this arrow is this. So if I shoot it all the way up, I'm getting full volume. If I shoot it down, 0. Get it? So, and you can see how this is kind of rubbing on the wires and getting connected.
Where did that come from?
It was manufactured.
Hmm?
It was manufactured.
I meant like, was that a part of the speaker system?
Oh, this one?
Yeah.
Oh, this is called a rheostat. It is meant to, this is actually meant to control the currents as a dimmer and stuff like that. So this is, in a circuit, if you want to control the current, yeah, this is one way of introducing it into the circuit. You can control the current. You can also use this. So they're all, this is typically a volume control type of thing. So you can actually choose it, but they're damaged. You can see the wires are out. So these are damaged. All right. You can just pass it around and have a look at it. So this is called a rheostat. Mainly, this one's job is to control the current. But I'm just showing you that this is also can be used as a potential divider. So if I connect 24 volts across from here to here and tap out from here to here, you will get different voltages according to where you place it. This is brittle, so take care.
Is that how light dimmers work?
Yeah. Yep. Now if you go to, sliding types, yeah. All the sliding controls, they're all the same thing. The same thing, but some of the sliding controls are semiconductors, so it will be much smaller. All right. What is the equivalent resistance? What is the equivalent resistance of a circuit shown here?
Sorry,
All right, 6 volts.
There's one of these on the test.
Was?
Yeah, with the triangle resistors.
No, they were easier.
Yeah, they were easier.
30, 18, 4.5. 30. Yep. So the question is asking what's the equivalent resistance of the circuit shown? That's the first question. In other words, what is the total resistance connected between the batteries from here to here? So before you do that, what you have to do is find out which ones are in series and parallel, right? Which ones are in series and which ones are in parallel? Can you find out which one's series, which is parallel? Are these two in parallel?
Yes.
No, in series.
Like when you consider them in parallel is like when you have opposite ends connected together. Yeah, so this end of the 30 and this end of the 30, are they connected to the 12? They are. This end of the 30 is connected to the 12. This end of the 30 is connected to the 12. So when they join hands in hand, then they are parallel. So these two are parallel. These two are parallel. So what's the difference between this being connected there or here? No? And what's the difference between this connected? So 12 and 30 are in parallel. Actually, this circuit is much easier than I thought. Okay. Okay. So what is the parallel combination of 12 and 30 alone? 12 and 30 in parallel. 12 times 30 or 12 plus 30. How much? 3.1.
Never mind.
No, it's 8.8.
I don't know, you tell me. 12 times 30, which is 360 divided by 42.
8.57. 1.528.
Okay, 8 point. So that is 8.57 ohms, and that 8.57 and 4.5 are in. So what's the total? So that is 13.07. So 13.07 is up to here, and those the 13.07 and the 18 are in. Go ahead. So that and the 18 are in parallel. So times 18 over 13, this thing plus that one. So that is 31.07. So 13.07 times 18 divided by 31.07. That will be the equivalent resistance. That's the first answer. That is the first answer. Questions here? All right. The second question is, what is the current in the 18 ohms resistor? What is the current here? Now for the current, you have to work backwards. So now you know the total equivalent resistance is how much? What is the answer?
7.572.
So since the total resistance is 7.57, what is the current driven from here? What is that current? 6 divided by 7.57 ohms.
0.79 amps.
0.79 amps. So 0.79 amperes is coming to this place here, and it sees that these two are in parallel. I can simplify the circuit so that you will see it better. The same thing, you can simplify it so that you can actually see it all the way better. Now see what I'm going to do to simplify it. Look what I'm doing to simplify it. I'm going to take the 30 from here and connect it here. And I'm going to take that and connect it here. Alright. It's the same thing. So, what is the current coming from here? 0.79. And when it comes here, it's going to split itself from here this way and this way, right? It's going to split itself. And as you can see that this current is going to be totally independent of that current. It's connected to the power supply directly. Are you sure this is correct? Oh, it's fine. So how many amperes is coming from here? How many amperes is coming this way is totally independent of that one. You see, look at this. 6 volts is coming straight across here. See, this end is connected here and this end is connected. So there's nothing to do here. What's the current? 6 divided by 18, which is 0.33 amperes. You got that? So the current through the 18 ohms is 0.33 amperes. Now when the circuit is rearranged, you can see it very clearly. Okay, so that's 0.33 amperes. How? Because this is getting 6 volts. 6 volts divided by 18 is 0.33 amperes. Out of 0.79 amperes, 0.33 goes this way. So what's this current? 0.46 amperes. Now that will help us in the next part of the question, which is, what is the current in the 12 ohms resistor? What is the current in the 12 ohms resistor? So you're going to do basically the same thing. This is going to create a potential difference from here to here. And that same current is flowing here. So you can figure out how many volts is here. What is 0.46 times 4.5? 2.07. Out. So from here to here is 6 volts. 2.07 is gone. What is here?